Hello, everyone. Today we're looking at direct proportion. Now, basically, the idea of direct proportion is, I'll use a highlighter to refer to this graph here. If the value of one of the variables is going up, the value of the other variable is going up at the same time, in the same rate. And a direct proportion graph will end up looking pretty much like that, meaning it'll be a straight line, it'll go through the origin, and we can easily calculate the rate of change. So let's have a look at a graph that's a direct proportion graph. Now this is a distance time graph. So distance time graph. Now they actually show the speed because this is showing a rate of change, how quickly the distance changes in respect to time. And as you can see, it works. It's a direct proportion graph because we have the going through the origin here. It's a straight line, and we can get a constant rate of change. So what the speed is actually the rate of change. It's just in particular for this distance time graph, speed, something that we use in our everyday life. So the average speed, is the distance traveled. Now, what is the distance traveled? We can draw it on here. We can see it up here. It has to go from there to there. How far is that? It goes all the way over to 100. Okay, so our distance traveled is 100 over the time taken. Well, the time taken was from 0 all the way up to 5. So our distance, our average speed is 100 divided by 5, which is 20, and it's kilometers per hour. So that's you're on a bike, that's a very long ride, 5 hours at 20 kilometers per hour. Now we can get a rule for this as well. So up here, in the information that was given before about it, which you've hopefully read, it says the rule is in the form y equals mx plus b, and m is the rate of change. So this is the rate of change, or the m. So let's have a look and see if we can work out the rule while we're here as well. So the rule for this graph would be, so it's whatever this one, the vertical graph is, so distance traveled, so let's call it D for distance traveled, is equal to the rate, we'll call it M or gradient, times the time traveled in hours. Now we know what the M is. The M is 20, we worked it out, so it's 20t. So distance equals 20 times t. So if I am traveling for 1 hour, 1 times 20 gives me 20, does that work after 1 hour? Yep, my answer is 20. Or if it was 3 hours, 20 times 3 would be 60, and that you can still see that works. So if this person continued, I must be getting a bit tired if you're on a bike, and was traveling for 7 hours, you could still see that 7 times 20 would be 140. You could work out beyond the graph how far they traveled. So let's have a look at this one. This is showing the number of pages read in hours of reading time. So let's find the gradient in the graph. Now remember, that's the rate. So I need to get the change in the vertical, so all that way up. So remember, it's the change in y over the change in x. So the change in y, I've gone from 0 all the way up to 200 over the change in x. Well, that was for 9 hours across both. So in 9 hours reading, I did 200 pages. So what's my average rate of reading? So I go 200 divided by 9, which is not a nice whole number, but 22.2 recurring. So that's my rate of reading per hour. So let's find a rule for calculating N, the number of pages read, given T, the number of hours spent reading. So N equals, remember it's M is the rate times the T in this case. So N is the number of pages that is read, T is the time in hours. So if I had my rule, it'd be N, I need my rate, which was 22.2 recurring times T. And that's my rule. I can put a times there if I'd like, make it clearer. Okay. Now, let's have a look at the question from your exercise book. So it's using the same sorts of information that we've just been talking about. Water is poured into an empty tank. It takes 3 hours to fill the tank with 6,000 litres. What is the rate that the water is poured into the tank? So let's have a look at the rate the water is poured into the tank. So let's do the change for the litres. We went from 0 to 6,000. So 6,000 over how long it took, 3 hours. So the rate is 2,000. Now it's litres for every hour. Okay. Now, question B, draw the graph of volume versus time. Now, time always goes over the horizontal, and we're going to go over 3 hours, it says. So let's pick something nice and clear. 1, 2, 3. And I'm going to always label my axes. So time in hours goes across the bottom. And on the vertical, I'm going to have my volume. And I'm going to say what it's measured in. It's measured in litres. Now I need to get to 6,000. So I need to look at my graph and think, well, what's a good way of breaking this up to go all the way up to 6,000? So I think if I use each big block to get to 6,000, I must keep it consistent. So I'm going to go up by 2,000. So that'll be, I choose my scales that I put on these here. So I then need to draw I want to go from the tank is empty at the very beginning of time. And at the end of time, after 3 hours, it's 6,000 litres. So here is where I'm finished. And I need to join it up with a straight line. Just wondering if I can draw straight lines here. I can. So there, all the way down to, got it. There's my straight line. So there is my graph. But see that I have got my, I've labelled my axes and I've shown the scale as well. So make sure when you're drawing a graph, you put information on the scale like I have there. And you also label your axes, which I did in that's highlighted in yellow. Okay, so next question is C. Find the gradient. Now the gradient you can see here again, just like we did before. The rise or the change in Y over the run. How far up over how far across. So the gradient, I may as well leave it in this color, is how far up is 6,000 over how far across is 3, it's 2,000. It's the same as the rate, and that's what we said was before. So I will get out using the highlighter, I think. Oh, maybe I won't. So let's go to question 2. Oh yeah, I am. Find the rule. The rule, well, we've got V is the volume. Now the rate, remember, is the M times the whatever's going the horizontal, that's time. Now the M we already know is 2,000. We worked it out, so it's 2,000 times T. That's our rule. Now, question D says use your rule. So I'm going to change colours. So question D, use the rule to find the volume after 1.5 hours. So that means we want to let T equal 1.5. So this is our rule, V equals M times, well, not M, sorry, we know what it is. We know it's 2,000 times T. So it's 2,000 times 1.5. Now, and you can't do that in your head. You get your calculator and you go 2,000 times 1.5, and that gives you 3,000. 3,000 litres. And we can have a look up here and see if it makes sense. So we went to 2.5, I think. So if I want to have 1.5. So I can have a look here and see if it seems to make sense to my graph. Look at that, I go across. It does seem to match up to find the 3,000. So that looks sensible, looks like it's working. Well, that was part 1. So part 2 says find how long it takes to get to 5,000 litres. So that means we need to let the volume to equal 5,000 litres, and we need to find the value of T. So remember, we're starting with the formula V equals 2,000 times T. So we're going to let the V equal 5,000, 2,000 times T. How do we get the T by itself? We divide by 2,000. Do the same to that side. That goes. T is equal to 5/2 or 2.5 hours. And again, let's go up and see if that makes sense. At 2.5 hours, here's 2.5 hours between 2 and 3. If we follow that along, where do we hit the graph at? Is that at the 5,000 litres? Has it made sense? Yep, that's the 5,000. It works. So now you can try the other questions.